Hello there, and welcome back. In the previous videos, we've primarily been focusing on hypothesis testing for the population mean mu. We've looked at confidence intervals, test statistics, p-values, one and two-tailed hypothesis testing for that particular parameter. Now we're going to change our focus to a different parameter, in particular the population proportion, which is simply just the percentage of a population that satisfies some desired criteria. So let's start off with a couple assumptions. So let us suppose that we draw some sample from some population, and this population need not be normal, but normality sometimes helps with a couple assumptions and approximations. So let's just assume that it's normal, and let's assume that this population has some mean mu and standard deviation sigma. So the proportion for a particular population is always going to be equal to P equals X divided by capital N. Some people will represent this as the number of successes in the population divided by the population size, but we're going to be focusing things from this perspective for now, but they are equivalent perspectives. So if we want to approximate this particular parameter, what is a reasonable point estimate for that particular parameter, we can approximate it or estimate it by the sample proportion, which we will abbreviate by p hat. So p hat is going to be equal to capital X divided by little n, where little n is the size of the sample. And of course, this is an equivalent perspective of, for example, little ns divided by little n, or the number of successes in our sample divided by the sample size. So a couple questions to start off with. For example, is p hat an unbiased estimator for p? We hope it is, and indeed it is. So let's just go through a quick proof of that. So what is the expected value of p hat? If this is equal to p, then all is well. So p hat, we know, is going to be the expected value of x divided by little n. We know 1 over little n is going to be equal to a constant, so we can factor out constants out of expected values. So we have 1 over n times the expected value of x. Now let's take a moment. What is the expected value of x here? So x corresponds to the number of successes in a sequence of independent Bernoulli trials. So let's assume that these are, of course, independent so we can execute that interpretation. So if we perceive x as the number of successes in a finite sequence of Bernoulli trials, that means x is going to be a binomial random variable. So a binomial random variable. So if x is binomial, then the expected value of a binomial random variable is just going to be equal to n times the probability of success p. And as we can see, these n's cancel, therefore we're just left with the probability of success p. Therefore we have that the expected value of the point estimate p hat is going to be equal to p, and all is well. That means we can calculate the standard error of the estimate for p hat as an approximation for p by finding the standard deviation of this random variable p hat. So let's start off by finding the variance, and then we can go ahead and find the square root of that to find the standard error of that particular estimate. So the variance of p hat is going to be equal to the variance of x divided by m. We can quadratically factor out that n to give us 1 divided by n squared times the variance of x. Since, again, x is a binomial random variable, the variance of that binomial random variable is going to be equal to np times 1 minus p. So we see that an n cancels out of this expression. Therefore, we have that the variance of this sample proportion is going to be equal to p 1 minus p divided by m. Therefore, the standard deviation of p hat is going to be equal to the square root of p 1 minus p divided by m. So keep in mind the standard deviation of a point estimate for a parameter is just synonymous to another perspective known as the standard error. So we have that the standard error associated to using p hat as an estimate for p is going to be equal to the square root of p 1 minus p divided by m. Now there is a little issue with this standard error because we actually do not know p. So p is not known in this expression. So what is a reasonable approximation for the standard error of this estimate? So since we're technically approximating p with p hat, we could replace p with p hat to get an estimate. So this is approximated by, not exactly equal to, the square root of p hat 1 minus p hat divided by m. Right? So that's an approximation for the standard error of the estimate. And some people will call this the Wald approximation. Now, is there a better way to go about this so we can actually use the actual analytical standard error of p hat in order to construct what eventually we will build as a confidence interval? The answer is yes. We'll talk about that after we discuss this Wald approximation because it at least is a little bit more easier to calculate. So now we have a standard error. So now we need a distribution in order to model probabilities. So for example, levels of confidence and levels of statistical significance and all of these things. So x, as we already know, is a discrete random variable, but not any discrete random variable, but it is a binomial discrete random variable. So how are we going to model the proportion? Well, keep in mind the proportion p hat is a continuous random variable. So we can't use a binomial random variable directly to model a continuous random variable. So is there any tools that we've discussed up to this point that is going to allow us to deal with this conflict? And the answer is yes. So recall the de Moivre-Laplace theorem. So the de Moivre-Laplace theorem says if n converges to infinity, then the binomial distribution, let's call it the binomial PMF for probability mass function, can be approximated by a normal probability density function where the mean of that approximation is going to be equal to NP and the standard deviation is going to be equal to the square root of NP 1 minus P, right? So if we're using approximations, then that would be P hat, and P hat approximations, right? So this is pretty much the key here. So that means we can also find z-scores for modeling our levels of confidence. So every time you're going to be using confidence intervals and hypothesis tests for proportions, we will always use z probability density functions for testing. But keep in mind, we only can use this confidently if we have evidence to believe that the sample size is large. And of course, we can include the finite population correction factor in the case that we do know capital M. But generally speaking, if n is small, then a lot of these approximations and interpretations are going to be very wrong. And we'll discuss that briefly. So now that we have a standard error of the estimate and a distribution associated to this representation of confidence, now we can start constructing our confidence interval for the proportion. So the C% confidence interval for population proportion P. So a point estimate, of course, is going to be equal to P hat minus the margin of error, and then P hat plus the margin of error. So that is our structure for our confidence interval for the proportion, where the margin of error is going to be equal to our z critical value times the standard error of the estimate for P hat. And what is the standard error of the estimate for P hat? That's going to be equal to the square root of P hat 1 minus P hat all divided by m. If you want to throw in the finite population correction factor, indeed you can. That's going to be capital M minus little n over capital M minus 1. But keep in mind you can only add that on or multiply that on if you know the population size, capital N. But generally, this is the starting point for confidence intervals for population proportions. And keep in mind, you should only use this, if n is large. So what is large? So there's actually a rule of thumb that a lot of practical people use. So let's just state that right quick. So just a rule of thumb. You should only use if 1, the number of successes in our sample is greater than or equal to 10. 2, the number of failures is greater than or equal to 10. So if both of these satisfy, then that requires that the sample size must be greater than or equal to 20. And, moreover, 3, p hat should be far from 0 and far from 1. So the sample proportion should be far from the boundaries of possibility of 0 to 1. Because remember, the probability of success can only range from 0 to 1. The normal distribution, z, ranges from minus infinity to infinity. So it's possible that your confidence interval, once you actually construct it, actually go outside of those bounds. So when you start having a probability of success for a sample that's close to these boundaries, you're going to start having a lot of issues and interpretations that are not possible. And of course, one important thing that you definitely should have is that these observations must be independent. Right? So if you're interested in looking at political viewpoints for a particular sample or population, make sure nobody's political opinion is influencing the opinion of the other. Else these results are definitely going to be very, very skewed. So now that we have a couple of the tools and a couple things that we definitely should keep in mind when doing hypothesis testing on the proportion, let's go through a particular example on how we would actually execute that particular hypothesis test with a confidence interval. So let's assume that we are interested in knowing the percentage p of a population that likes dogs. You can replace this animal with any other animal that you like, and you can change these numbers to, fit your interest of modeling. So let's assume that we're interested in the percentage that likes dogs. So what are we going to do? So we're going to go out, grab a sample from that population, count how many people in the sample like dogs, divide by the sample size, let's assume that's 43, and we get some percentage of 62%. Now sometimes this number of successes is not an integer. Sometimes this percentage is approximated via some other models, so sometimes those do not necessarily line up. For example, in this case, you'll find that ns is actually not an integer. But let's just assume that everything is working appropriately. So let's assume that the claim is that 80% of people like dogs. So let's go ahead and choose a two-sided alternative that p is not equal to 80%. So if our sample proportion p hat is significantly larger than 80%, but of course not bigger than 1, or significantly less than 80%, but of course not less than 0, then we have evidence to believe that this null hypothesis is true. Now, of course, you can do a one-sided alternative, and of course that will follow similar to our one-sided hypothesis testing for the sample mean, but we won't get into it here. Let's assume that we want to commit a type 1 error 8% of the time, so we're going to be letting alpha be equal to 8%, forcing our level of confidence to be 92%. How would we go about constructing a confidence interval for the population proportion and then concluding this hypothesis test? So, quick solution, not quite hard. So the very first thing we need to do is have a distribution that models our level of confidence. So this is going to be a z distribution, always with a population proportion. You're never going to be using t for proportions, so that's a good thing. So you can use z tables or percentiles for standard normals, whichever one you prefer. And this is going to be two-sided. So there's going to be some critical values that are going to be dictating this particular area. Right, so we want this area to be equal to 92%. So there's going to be a z critical value that's going to create the upper boundary and a negative z critical value that's going to dictate the lower boundary. So one should be able to find by now that this z critical value for a two-sided symmetric 92% confidence interval is going to be approximately equal to 1.7507. Once we have our z critical value, then we can calculate the standard error of the estimate associated to using p hat as an approximation for p. So the walled approximation for the standard error for not x bar but p hat is going to be equal to the square root of p hat times 1 minus p hat divided by m. Once you replace p hat with 62% and n with 43, then you're going to find that this is going to be approximately equal to 0.0740. Keep in mind that this is a percentage. Once you have your standard error of the estimate, now we can construct our margin of error for our confidence interval. So our margin of error is going to be the product of my critical value and my standard error of the estimate. So that's going to be approximately equal to 0.1296. So we have a margin of error of approximately 13%. So I have my point estimate of 62% and a margin of error of 13%. Therefore, I can construct my confidence interval. So my 92% confidence interval for the population proportion p is going to be p hat minus epsilon, so that's going to come out to approximately 49%, and an upper boundary of 75%. So that's my confidence interval to the nearest percent, And remember, our null hypothesis was that the population proportion P was equal to 80%. Since 80% does not belong to this particular interval, we're going to be rejecting the null hypothesis. You can do similar things, for example, with test statistics and p-values for proportions, but we're not going to get into them here. So now we have a confidence interval or approximation of 1 for the population proportion p hat. Now keep in mind that this is not the exact standard error of the estimate for p hat for p. It is just an approximation of it, because originally it was p, not p hat. Also, just be aware that there is an alternative representation of this in terms of the number of successes and the sample size, and you should be able to verify this on your own, because p hat is just the same as the number of successes divided by the sample size m, and you can rearrange the other expression in a very similar way. So that's going to be equal to plus or minus the z critical value, and then you're going to have, let's see, the sample size times the square root of the sample size. So the square root of sample size is on the bottom. The p hat, 1 minus p hat will also have an n. When you multiply the two square root of n's, you're going to get an n outside. So that's where that n square root of n term comes from. And then you're going to have the square root of the number of successes times the number of failures there. So you should be able to verify that that is indeed the same exact formula. So these are two equivalent perspectives of the confidence interval. A couple other observations that you should be aware of. So this clearly is symmetric about the estimate p hat. So that's usually a good thing. It's usually easy to interpret. But there are several downsides to this. And the downsides are generated by using this as our standard error. So let's quickly talk about them. 1, p plus epsilon could be above 1. Unrealistic. 2, p hat minus epsilon could be below 0. Also unrealistic. 3, it's not reliable if n is small. That's a result of the de Moivre-Laplace theorem, approximation for modeling the distribution of the number of successes with a binomial distribution and approximating with a normal right after. And 4, it's not reliable if the number of successes or the number of failures is small, because that implies that the probability of success is close to 0 or close to 1, which will generate issues with, for example, the first two things. So how can we fix these issues? Well, the obvious issue is to fix, this standard error of the estimate for p hat. So how are we going to go about that? So let's just make a couple of analytical observations that we've actually discussed so far. So remember, p hat minus p all over sigma p hat. Does this formula look familiar? Well, it should. It's similar to the formula for x bar minus mu divided by sigma x. So it's practically a z-score for a probability of success. So if this is associated to a z distribution, this should also be associated to a z distribution too. Also, the standard deviation for p hat is equal to p times 1 minus p times 1 minus p all over n. Remember, this is the standard error of the estimate for p hat, the analytical one, not the approximated one. So we have these two things that are true. So is it possible that we can combine them into the same exact formula and possibly solve for what value of p will make this true? And the answer is, of course, yes. So what we can do is do the following. Let's see. So let's just begin by noticing we have a sigma there and a sigma there. So let's just isolate this right-hand side for the first formula. So we're going to have p hat minus p is going to be equal to z, so that's going to be your z critical value in disguise, but I'm just going to call it z eventually, times sigma p hat. But sigma p hat is just going to be equal to that square root term. So square root of p times 1 minus p all over n. So once I combine these, possibly I can solve this equation for p, and I might be able to get something very, very useful out of it. So I have this is equal to that, so that gives me p hat minus p is going to be equal to z times the square root of p 1 minus p all over n. So our goal is to find a representation for p. So let's solve this equation for it. Radicals are not good, so I'm just going to square both sides of this equation. So this square is going to apply to the square root, and that's z. And what are we going to have? So I'm going to have p hat minus p squared equals z squared times p 1 minus p all over n. And then I can distribute this p hat minus p term by using, foiling or whatever method you're familiar with. So that's going to be equal to p hat squared minus 2p hat p plus p squared equals z squared p 1 minus p all over n. Now I'm going to get rid of that fraction by multiplying both sides by n. So that's going to give us n p hat squared minus 2n p hat p plus n p squared equals z squared p 1 minus p. And then I'm going to distribute, so that's going to give us what? So z squared p minus z squared p squared. And then I'm going to move these terms to the left-hand side of this equation, and I'm going to group my terms of p together. So I'm going to have this p squared term and that p squared term, and then I can group them together eventually. So what is that going to give me? So that's going to give me z squared p squared plus np squared. And then I'm going to have my p terms. So that's going to be that term and that term. So let's just group them together. So that's going to be plus z squared, that's going to be minus actually. So minus z squared p minus 2np hat p. And then I'm going to have the other term that's sort of just chilling there all alone. It's kind of sad. So p hat, the quantity squared, is equal to 0. And then I'm going to factor wherever I can. And you're like, whoa, where is he going to go with this? So it's going to be m plus z squared times p squared. And then I'm going to factor a negative, and that's going to be 2np hat plus z squared p plus n p hat squared is equal to 0. So what I'm going to do is I'm going to call this a, call this b, call this c, and then I'm going to have ap squared plus bp plus c equals 0. So this is a quadratic equation. So how do we solve quadratic equations when the terms are not necessarily nice? The key, quadratic formula. So remember, to solve for p, that's going to be p is going to be equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Now this might look a little bit scary, but b squared might not be very easy to do, but I definitely invite you to if you are feeling very adventurous. So actually once you substitute b, a, and c into this formula, 10 hours later, you're going to have p is equal to 1 over 1 plus z squared over m times p hat plus z squared all over 2n plus or minus z all over 1 plus z squared over n times the square root p hat 1 minus p hat over n plus z squared over 4n squared. Now that looks scary. But take a moment and actually look at what we have here. So we have a plus or minus, so technically we have almost like a confidence interval, right? Because we have sort of an estimate for p hat, plus or minus a margin of error of some sense. It's just not pretty, right? So maybe we can represent this in another way that's a little bit more friendly to look at. So if we actually look at this from the perspective of the number of successes and number of failures in our sample, the representation for this is actually quite very nice. So let's just look at that and see what that's going to go into. So one can show that p is going to be equal to the number of successes plus 1/2 z squared all over n plus z squared plus or minus z all over n plus z squared times the square root, number of successes, number of failures, all over n, plus z squared over 4. And that is actually pretty nice. So what do we have here? So I'm going to call this term p hat w, and then I'm going to call this term epsilon w, And then I have that P equals plus or minus P hat W plus or minus epsilon W. So now I have what I call a Wilson score confidence interval for the population proportion. So a Wilson score confidence interval for the proportion P. So what is that? So that's going to be equal to CI, and how you denote it, it doesn't really matter. I'll just call it CIW. C percent for P is going to be equal to P hat W minus epsilon W, and then P hat W plus epsilon W. And I'm just subscripting the W's to just sort of distinguish it from the old, not reliable confidence interval for the population proportion. Now that we have this new and better confidence interval, let's do an example of how we would actually calculate it and interpret it. So let's consider a similar example to what we did before. So let's assume that someone claims that, again, 80% of people like dogs, and let's assume we are going to choose a two-sided alternative hypothesis for this claim, and let's assume that the probability for committing a type 2 error, alpha, is 8%. So if we let alpha be equal to 8%, so that means we're going to be constructing a 92% confidence interval for the population proportion P that we're seeking to test. We're going to go out and gather a sample. Let's assume that our sample size is 54, and the number of successes in that sample is 43. So of course the P hat for this is going to be equal to the number of successes divided by M, so you can find that that's approximately equal to 79.6% for the sample proportion P. So now let us go ahead and construct our Wilson score interval for the population proportion, which is very, very more sustainable and appropriate. Even though the sample size is relatively large and the number of successes is pretty big, one may argue that 79% is close to 1 or 100%. And if that is true, then Wilson score may be more appropriate. But generally speaking, regardless of the scenario, Wilson score is always a safe way to go. So since C is 92% and we're doing hypothesis testing for the proportions, we're always going to be using a Z distribution to model critical values. So our Z critical value is going to be that 1 plus C over 2th percentile. And you can find that the Z critical value, which is the same as the last example we did, right? So that's going to be 1.7507 for our Z critical value. Now, if the number of successes in our sample was 43 and our sample size was 54, that means the number of failures in this particular sample is going to be 54 minus 43, which is going to come out to 11, because we're going to need that in our nicer representation for the Wilson score interval. So now let us calculate our middle of our confidence interval. So P hat W, which is going to be, again, NS plus 1/2 the Z critical value squared divided by N plus Z squared. So once you actually plug in the number of successes, the Z critical value that we have calculated, so that's going to be that squared, and then on the bottom is our sample size plus the Z critical value, again, the quantity squared, one can find that that's going to be approximately equal to 0.7804. So this is going to be the middle of our Wilson confidence interval, right? So that's a middle. So keep in mind that the Wilson confidence interval is not symmetric about P hat. It's symmetric about this, modified P hat value, right? And there's a lot of analytical things behind it, but generally speaking, it's not centered around P hat. It's centered around a modified or a corrected P hat value, if you may. So now that we have the center of our Wilson confidence interval, now we need the margin of error for this Wilson confidence interval. So again, it's going to be the Z critical value divided by the sample size plus the Z critical value squared times the square root, number of successes, number of failures, all over sample size, plus the Z critical value squared divided by 4. Once you actually calculate those calculations, you're going to come out to 0.0947. So that's the margin of error for our Wilson confidence interval. Once you calculate all these things, that means our Wilson confidence interval for the population proportion P under a 92% level of confidence is going to be approximately equal to 0.6857. So P hat W minus epsilon W, and then P hat W plus epsilon W, 0.8751. So that is our conclusion. So remember that the null hypothesis was that the population proportion was equal to 80%. Since 80% belongs to this particular interval, that means we're going to be failing to reject the null hypothesis here. And keep in mind, this is not a different conclusion from the other one because I'm referencing a different sample. Because remember, if you calculate different samples, it's possible that your conclusions are going to be completely different. So that's pretty much what we're looking at here, right? Now, even if you did have the same exact sample, it will be possible that the Wilson and the standard confidence interval will generate different conclusions, because especially if your null hypothesis claim is on the boundary of one of these, definitely a slight manipulation will cause a different outcome. So when you actually go into those particular scenarios, it's usually best to rely on the Wilson confidence interval for interpretations if by chance the other one is generating a different conclusion. But generally speaking, Wilson confidence intervals are better than the walled approximation version for the standard error of p hat, so when in doubt, use Wilson. Anyway, that's just an introduction to hypothesis testing for the population proportions. In the next video and discussion, we will discuss how to do confidence intervals for the population variance and standard deviation. I'll see you there. Take care.